Hello, chemistry students. Today we're going to be talking about solution stoichiometry. So the idea here is that not all substances that you use in a lab are going to be solids that you can weigh on a scale to get their mass. A lot of the chemicals that you can buy are actually solutions that have concentrations. But luckily, we can use the concentration of a substance and its volume to determine how many moles are contained within it to help us do our stoichiometry problems. For example, say we wanted to know how many moles were in 80 milliliters of a 0.6 molar solution. Well, first we'd turn our 80 milliliters into liters, so that'd be 0.0800 liters. And then we'd use molar in terms of moles per liter, so that when we multiply it by the volume, the liters cancel out and we get units of moles. So then we do 0.08 times 0.6, and we end up with 0.048 moles that would be contained in 80 milliliters of a 0.6 molar solution. So we can apply this logic to stoichiometry problems as well. So say we had this problem here. What volume in milliliters of a 0.155 molar solution of hydrogen sulfate or sulfuric acid would be needed to completely neutralize, remember that means a complete canceling of acid with a base, with 75 milliliters of 0.255 molar sodium hydroxide. This is going to be our base in this situation. How many grams of water are produced? So we have two things to solve for. First, we want to solve for the volume of the sulfuric acid and then the mass of the water produced. So first, let's get our balanced chemical equation. This is always the best first step for a stoichiometry problem if the balanced chemical equation is not given. So since this is an acid-base reaction, sulfuric acid is going to react with sodium hydroxide, and there's going to be a double replacement. The sodium is going to go with the sulfate, and then the hydroxide and the hydrogens are going to combine to make water. And we're going to need to have a 2 in front of the water in front of the sodium hydroxide to make sure that everything is balanced. So that tells us that the sulfuric acid or hydrogen sulfate and the sodium hydroxide are reacting in a 1:2 ratio. Next, we can get into the actual stoichiometry. We know that sodium hydroxide is our known quantity since we know both its volume and its concentration, and we're trying to solve for the volume of this sulfuric acid solution. So we'll start with the sodium hydroxide. We take our 75 milliliters, convert that into liters, multiply that by 0.255 moles per liter, its concentration. And that tells us that we have 0.01913 moles of sodium hydroxide. And then from here, we can determine the moles of the hydrogen sulfate based off of the balanced chemical equation. We know that it is 2:1. So if we multiply it by 1 mole of hydrogen sulfate over 2 moles of sodium hydroxide, we end up with 0.009563 moles of the hydrogen sulfate. However, we want to get the volume of it. So we're going to utilize its concentration in moles per liter as a conversion factor to do so, much like we did earlier in the slides. Except this time, we're not going to have it in moles per liter. We're going to flip it upside down so that it's liters per mole, so that moles will cancel out and we'll get units of liter. This is totally okay to do. A concentration is a relationship between volume and concentration, or volume and moles of solute. So it can be oriented either way depending on what type of conversion you're trying to do. So we have our 0.009563 moles of our hydrogen sulfate, and then we multiply that by 1 liter over 0.155 moles. The moles cancel out, and we get a volume in liters, which is 0.06169 liters. And then we can multiply that by 1,000 milliliters over 1 liter, which I didn't show here, but that's how you convert the liters into milliliters. And we get a total of 61.7 milliliters, which tells us that's how much of the hydrogen sulfate solution with this concentration that we have to combine with 75 milliliters of this sodium hydroxide solution to get complete neutralization. And then the other part of this question is we had to figure out how many grams of water produced. Now, this is going to be like a normal stoichiometry problem where you take the moles of the thing that you know, multiply it by the ratio. In this case, the sodium hydroxide and the water are 1:1 since it's 2:2 here. That gives us 0.01913 moles of the water, and then we can just convert that to grams by multiplying the moles by the molar mass of water. We get 0.345 grams. All right, and if we were to show this all in one-dimensional analysis chain, it would look like this. And just as a note here, this is the second step where we got the grams of water. That would be inputted at this part in the chain if you were to solve that problem instead. All right, now let's go over a bit more complicated of a problem. How many grams of precipitate are expected to form when 125 milliliters of a 1.333 molar potassium iodide solution is mixed with 125 milliliters of a 0.855 molar lead-2 nitrate solution? And then also, what is the concentration of leftover nitrate at the end? So as you can see here, we have a volume and a concentration, and then a volume and a concentration, and we're trying to figure out the amount of precipitate being formed. So we're going to first have to figure out what the precipitate is, and then since we have a set amount of both of our reactants, we're going to have to treat this like a limiting reactant problem. So first, let's write our balanced chemical equation. These are both ionic compounds, so this is going to be a double replacement reaction. Potassium iodide is going to react with lead-2 nitrate to form potassium nitrate and lead-2 iodide, and it's going to be in a 2:1 to 2:1 ratio. And then if I look at my solubility rules, I know that potassium things are always soluble, nitrate things are always soluble. So that leaves that potassium iodide as our insoluble salt. And we would know that because the halide rules for iodide, chloride, and bromide, they're always soluble unless combined with silver, mercury, or lead. And we have lead here, so this is going to be our precipitate. So much like a normal limiting reactant type problem, we're gonna figure out who is the limiting reactant first, based off of how much we need to react with each of the reactants. So I took my volume here in liters, multiplied it by the concentration in moles per liter for the Ki. I got 1.16663, and then I multiply that by 1/2. That's the ratio of the Ki to the lead-2 nitrate. And that tells me that I need 0.083313 moles of lead-2 nitrate to react with all of the potassium iodide. I do the same thing with the lead iodide in volume and concentration, and I get 0.1069 moles of lead-2 iodide, which we can see is more than the amount of lead-2 iodide that we need to react with all the potassium iodide, which gives us a clue here that the potassium iodide is our limiting reactant and the lead-2 nitrate is our excess reactant. But let's further prove that by continuing the reactant analysis here. Multiply that by 2 moles of Ki over 1 mole of lead-2 nitrate. And that tells us that we would need 0.2138 moles of Ki to react with all of the lead-2 nitrate, which we can see here is more than we have. So that's why I put a check mark here and an X next to this, because we're not going to be using this value, but this value is correct in terms of the amount of lead-2 nitrate actually being used. And since the potassium iodide is our limiting reactant, I'm going to then move that forward with the ratio to the precipitate to figure out the mass of the precipitate being formed, which is what I did in this last step here. It is a 2:1 ratio for the Ki to the lead iodide. So I have 1 mole of lead-2 iodide over 2 moles of Ki, and then I multiply that by the molar mass to turn it into grams, which is 461.01 grams per mole. And then I end up with 38.4 grams of lead-2 iodide. Now, the second part of this question, what is the concentration of leftover nitrate at the end? This is a little bit more complex to answer. At least we have to think about the situation a little bit harder. The at the end part is important because this is a mixture of two solutions. We started with 125 milliliters of one solution and then 125 milliliters of another solution, and then we mixed them together. Also, we need to consider the chemistry. Nitrate is a spectator ion in this case. None of the nitrate is being taken out of the solution to make the lead-2 iodide solid. So basically all of the nitrate that we started with is still there at the end. So it's just a matter of finding out how many moles of the nitrate we have and then dividing that by the total volume of the solution. So I do that here in this next problem, or this next example. I took my moles of lead-2 nitrate, because that's the source of the nitrate. And I know that there's 2 nitrates per every 1 lead-2 nitrate. There's 2 of those individual polyatomic ions per every 1 of the compound. So that tells me that there's a total of 0.2138 moles of nitrate overall in the solution. And then I want to divide that by the volume of the solution, which started as 125 milliliters, but since we're saying this is at the end of the reaction, we're assuming that we mixed those two solutions together. So 0.125 liters plus another 0.125 liters means that the volume of the new solution, that is the mixture of the two solutions, is going to be 0.250 liters. So then I take those moles of nitrate, divide it by the total volume, and I end up with 0.855 molar nitrate at the end. And one quick note about this, we were looking for the concentration of leftover nitrate in this one, and nitrate happened to be the spectator ion, so none of it was consumed in the reaction. That's not always going to be the case. Sometimes the leftover ion that you're trying to find the concentration for will have been partially consumed to make the precipitate. So you will have to figure out how much of it is left in some cases, and then still divide that by the total volume. But that is all I have to say for this one, and I'll see you in the next video.